Hey folks. So we'll be doing this for a few days. um, Today, I'm just going to advance our knowledge just a little bit, okay? I feel nervous giving you too much when I'm not there to ask questions to. But we'll see. Maybe this will work if I just give you like a little bite size portion and you can tell me if it doesn't make sense or whatever, and then we can adjust, okay? Um, so, look, you've taken notes today already, and so you know what antiderivatives are. They're often called indefinite integrals, um, as opposed to definite integrals, which have like the limits, right? Those mean actually area, caterpillar's crawling and getting rectangles on her back. And you probably have already noticed that finding antiderivatives is way tougher than finding derivatives. And so today, I want to just tell you one technique that they have developed that helps you find an antiderivative that otherwise looks impossible. Um, if you're interested, there's a few techniques that they developed over the centuries to unlock antiderivatives that look impossible, but then you can like actually get them if you know the techniques. We only in our AP Calc class only need to know one of those, okay? One of those techniques to find antiderivatives is called U substitution. Okay, U substitution. And like I said, we're only going to do a little bit of it today, all right? So here, check this out. So there I have a derivative, an integral, and it probably looks somewhat imposing. U substitution, this technique, actually works really well with things that came out of the chain rule. And so we're going to sort of undo the chain rule by the time we're done fully explaining this. Like I said, I'll only do a couple steps today, okay? So what are the steps I'm going to do today? All right, look. Do you agree that it would seem to be useless right now, but do you agree you could just rename any part of this function with a different letter and then just rewrite the integral? Here's what I mean. Check this out. Like, not that it makes any sense to do this, but let's say that I said, how do I write so you can see here? Let's say that I said, oh, you know what? I'm going to have u of x equal x cubed. And so then, if I were to rewrite this, oops, that's supposed to be an integral sign, 3x squared times the sine of u of x dx. Do you see what I just did there? Like, I just substituted in. That's all, right? And so, like, it doesn't help at all. I could totally see why you'd be puzzled by that, but it's not illegal, right? So, great. The other thing that I want to ask you is this. Can you solve for du? What do I mean by that? Watch. If I take the derivative, now I've renamed part of the function for a random reason we don't get yet, but if I take the derivative of this, do you agree I get du dx on this side? And that equals 3x squared. So I haven't ever really talked about dy dx or du dx now as a fraction, but in fact it is. And it makes total sense to just, if you need what du is, just multiply both sides by dx, because that'll get rid of it over on that left-hand side. So, I'll actually show the step here. I would never usually write this, but if I multiply this side here by dx, and that means I have to multiply this side by dx, these two cancel. And so you're just left with du equals 3x squared dx. Okay? This is literally all I need you to be able to do for today's new learning, is to figure out what a good u is, and then once you have that u, to solve for du. Now, the question that you should be asking yourself is, how do you know what part of the function should be your u? That is the beautiful question to ask. Here it is. If you can see that one part of the function has its derivative in another part, then that is your u. Let's see how this plays out. Hey everybody, look at this right here. Do you see any part of this function that has its derivative in another part? I do. Ooh, look at I should use my multicolors here. Look at this x cubed here. Does it have its derivative somewhere else in the function? You're darn right it does, right? So then that's your u. So you would say u of x, I know I already wrote this, but now you'll know why I did it, okay? U of x equals x cubed. And look, do you know how like when we set up u's and v's for derivatives, you know how we kind of like just write u and v? They often do that here. So if you don't mind, I'm just going to write it the way that normally people would see it. They'll just say, oh, they'll just drop this x part, and they'll just write, oh, the u equals x cubed. And then don't forget, when you try to find what du is, our second step, you'll get du dx on that side, 3x squared on that side, that's a 3. And then to get du by itself, just multiply by dx. And I'm going to stop. Like, that's all I need you to be able to do. Figure out what the u is, and then solve for du. Can I, like, just give you a couple more examples, though? Like, let's say, in fact, you know what? I'm going to do this. Let's just say I have basically the same function. I'm just going to do one thing. Let's say it's x squared plus 10. What is my u? Well, if you remember, I know this is a mouthful, but if you remember, what's your u? Well, it's the part of the function that has its derivative elsewhere in the function. So I would totally understand if somebody was like, well, then you haven't changed anything. We're just going to have our u be x cubed again, because look, that's going to be part of my function. And I'm just going to tell you this. The reason I put this up here was there's a way better u to choose. Look at the entire parentheses there. X cubed plus 10. Do you agree if you take the derivative of all of that, including the plus 10, you still just get 3x squared? So usually you want your u to be as big as possible, okay? So don't just stop at x cubed. Do this, all right? That will make your life easier in steps we'll do tomorrow. And then I solve for, when I take the derivative, the 10 goes away, doesn't it? And du equals 3x squared dx. Okay? And that's it. Like, then I'm just going to stop. Can I just give you a hint here? Your u will often be in parentheses, like here. It'll be sometimes in an exponent. It'll sometimes be under a square root sign. Those are all classic places to find the u. It's usually just grouped off by itself somehow, okay? So let me just give you a couple more examples. Let's say we have stop the video and see if you can figure out what your u is here. Hopefully you can see that. That's probably better, right? Okay, so I see that, oh, this part of the function has its derivative elsewhere, so that's my u. And then I solve for du, and I get this. Shazam. Done. For now, it's done, okay? Let me give you another one. Bam. Let's say that I have 4x cubed, and then x to the 4th plus 7 raised to the 5th power. This is totally obnoxious, man. You ever try to get this derivative? Forget it, right? I'm sorry, this integral? Forget it, right? But let's just pry it apart. Do you see what a good u might be? I see it in the parentheses, just like I talked about earlier. The derivative of this guy is elsewhere in the function, so this is my u. U equals x to the 4th plus 7. And then, do you mind, like, can you keep up if I just write this? I just, like, did 2 steps in one here where I did du dx. Oops, my screen just faded here. And then I did du dx, then I multiplied by the dx, okay? Let's do a trig one. Last one, okay? And then I'll let you go do work. Tan x secant squared x dx. See, stop the video and see if you can figure out what a good u is. I know my trig derivatives because the derivative of tan x is secant squared, so this is my u. U equals tan x, so du would be secant squared x dx. Okay? I think that's enough probably to get you started on the worksheet that I assigned. And then if not, holy cow, just let me know, email or whatever, okay? Good luck.